So first off, who here is doing something with machine learning or AI right now? It's like you're thinking, oh, wow, fantastic. All right, next question, who here is a software tester? You're wearing a suit, I feel it. Oh, no, okay, now you're doing this. Anyway, if you were a software tester, then we'd be brothers or sisters, but that's okay. So I'm talking about the testing and quality of ML systems because in traditional software development, software testing is a more popular, more common field. We have lots of rules, we have lots of terminology, lots of things, and inside of the machine learning world, not so much. It's like we're kind of catching up in how you do quality of these systems, right? So real quick, a little bit about me. I apologize, a little bit hard to see, but I'm currently the head of engineering at an AI company. Before that, I was an engineering manager at Adobe. We did automation and productivity engineering, and that's where we started, or I started in machine learning. TestAutomationu.com, I'm an instructor there. This is a completely free platform. If you're interested in software testing or test automation, I would go check it out because it's pretty cool. And I do have a course that goes into more code-based examples of what I'm going to be talking about today. And then a bunch of other stuff too, but the last bit is QA at the Point, which is the software testing and quality organization in Utah. It's where I'm come from, so USA. I wish I spoke Italian because it sounds really cool, but I don't. But I speak Spanish, so I was able to talk to some people, kind of. But all right, so going into it. Back in 2019, Tulsi and Jacqueline at Google I/O said this: we need to test early and test often as machine learning engineers and as data scientists. And in 2019, this was a revolutionary concept. It was one of the first times that these experts in the field were talking about not just validation and recall or precision or any of that. They were talking about testing of behaviors and testing risks and quality of things. And so it's almost as if 2019 was when things started from, let's pull more stuff from traditional development and bring it into machine learning. So let's take a simple example for prediction. Let's say that we are the AI team at this grocery store chain, and we have the task of predicting how much customers would spend. This is the data set that we have access to. We have the number of people that come in, and then the purchase amount. So one person came in, they spent 10 euros. Two people came in, they spent 20. Four people, 40. My question to the audience is, how much do you think 3 people would spend? $30, right? How did you come up with that answer, and how did you come up with it so quickly? At one conference, I heard linear regression as like a collective. I was like, whoa. You're right, mathematically, yes, you're right. Well, you found this magical number of 10, which described the relationship between both of these columns. And so when you got the number of 3 people, you multiplied that by 10, and you predicted 30 would be the output. Using that same pattern, well, if I gave you 5, even though we've never seen 5 people, 57 would be 70, so on and so forth. Okay, not too bad. So when we talk about traditional programming and machine learning, in traditional programming, you provide the rules, you provide the data, and then you output an answer. So let's say we had a function that was like, is even, and you pass in an integer. You would define the rules to say whether the number is even or not and return that value. So when you're writing tests for it, let's say with like PyTest, well, it's pretty straightforward. I'm going to pass in 3, assert that it is not even, right, or assert false or something like that. When it comes to machine learning, well, what's the guarantee that 3 people are going to spend $30? There is no guarantee. They might spend $28. They might spend $33. They might just go to the bathroom and then leave and spend $0. That's where machine learning is a little more difficult to test because you're no longer dealing with a very black and white answer. You're dealing with these patterns, these relationships, these rules, right? It's a little bit different. But we can still apply a lot of what we do in software testing to machine learning. So before I move on, I wanted to point this out, where when we're doing like things with the weights of parameters, yes, you can test those things and tune these things, but that's not what I'm talking about in this presentation. The first thing that we actually care about is this data set, because the entire answer that we got, which was that for 3 people was 30, the whole answer came from this data set. And so the data is one of the first things you're going to want to test. So in the world of software testing, we have this concept that we call shift left. Who's heard this term before? The tester, yeah. Yeah. So shift left is a very, very common term in software testing. And in traditional software development, it's becoming more unpopular as well. The whole idea of shift left is let's take the SDLC, the software development lifecycle, which is usually like a big circle, right? And we flatten it out, where on the far left, we have design and business and requirements gathering, and on the far right, you have deploying to prod and observing and operating and that kind of stuff, right? So if we can bring our software testing, quality, risk-based thinking, systems design, all the good stuff, as far early as we possibly can to the left, we're going to prevent a lot of issues because we're thinking about these things as early as possible. As a machine learning engineer, it would be nice if I could be part of the requirements gathering rather than the business just throwing requirements at me and then me having to figure things out at that point. I could probably prevent a lot of things if I was in the room a little earlier, right? So that's the concept of shift left. So let's take a scenario. Let's kind of say if we were building a machine learning project from scratch, what would the steps be for us in order to create something that is hopefully helpful, right? So what you're going to see is a lot of questions that we're going to start asking that is going to be talking about a lot of risk and different ways that we're going to approach this. So defining the problem. The first one is, what are we trying to solve? In the grocery store example, we talked about how much customers would spend. Who thinks that's a good problem statement? How much customers would spend, okay? Why is that a valuable problem statement? What makes it a good problem statement? Or a high quality problem statement? Oh, shoot, we're tying it back. Well, it's difficult to say what we're actually trying to solve with that. Predict how much customers spend. Okay, if I'm able to predict that, what am I doing with that information? How is that actually adding value to my business or value to my customers? If I can predict that 3 people spend 30, whoop-de-doo, like, what do you do with that, right? So what if instead we change the problem statement to say we want to predict how much people will spend so we can prevent overstocking and understocking? Let's say that we want to make sure that to prevent understocking, which would be I buy 10 gallons of milk, 100 people come in, and there's not enough milk, so I'm going to lose all that money because I don't have enough milk. I've understocked on milk. Shoot. Overstocking is the opposite problem. I buy 1,000 gallons of milk, 100 people come in, now I lose 900 gallons because milk is a perishable item, so eventually I have to throw it away. So now I lost money on that side, right? So if our problem statement was, let's predict how much people are going to spend so we can stock the right amount and prevent understock and prevent overstock, well, that becomes a much more valuable problem statement, right? So what are we actually trying to solve? Who's the ML system for? Is this going to be for the regional manager? Is this for the night crew that's stocking? Is this for who's going to be using the ML system? One of my favorite questions is, does this even need machine learning, especially deep learning? Right, nowadays, deep learning is very easy to do. You get people like Carlos, who doesn't know the data science behind a lot of things, and yet I can, in like 5 lines of code, have something working for me that's deep learning, right? Well, how do I know that's good or not? Do I even need that much power? Right? Let's take the is-even example. You're probably not going to apply machine learning to that function, right? Step number 2 is to define success and assess risk. So you define initial baselines. In other words, you have to say what are the things that are going to indicate whether we're on the right track or not, right? So it might be that you need to make sure that your product or your model predicts something in under 5 seconds. Is that true? What if it was 1 second? Is that awesome? If it's 10 seconds, is that okay still? Things like that you have to define, because otherwise you're kind of just building something without any sort of measurements as to whether it's going to be good or not. We're dealing with data, of course, so consider privacy and security risks. Create a proof of concept. This is one of the biggest steps that people miss, is they go straight to trying to solve the problem without creating a proof of concept to say, what if just doing an ensemble learning method gives us 60%? Well, that could be our initial baseline. Any more work that we do on top of that should always beat 60%, right? So having a proof of concept also helps in this as well. And one of my favorite questions, do we even have the proper resources to do this? If we're building an ML system to detect cancer in people's hearts, again, Carlos Kidman, I'm the worst person to tell you whether that's high quality or not, because I know nothing about detecting heart cancer. So I would rather have experts cardiologists, doctors who do this for a living that have this expertise and experience to join my team so they can help us in defining these initial baselines and saying, are we on the right track or not? I don't want to go to like 12 years of doctor school just to do that, right? Maybe you do, shoot, make a lot of money. All right, the initial architecture. Which databases or tables are we pulling things from? What does our ELT process look like? Is this going to be behind a REST service, or it's going to be on a mobile device? And of course, how are we going to monitor and measure our model during development and post-deployment once it's in production? So all these kind of questions we have to be thinking about from as early as possible, right? That shift left mentality again. By the way, how we test these things changes drastically depending on some of these answers. Right, number 4 is collect data. All the data scientists are like, yeah, finally. Where's the data coming from? This is a little bit different. What I mean by this is like, are you gathering data from heart scans? Are you grabbing data from traffic cameras? Where are you grabbing the data from, right? Is this going to be different than your staging or development environments? Where are we storing the data? Is the data being streamed? Is it being batched? If it is being batched, how does that work? You might be tracking sessions, and you might be batching sessions. What if 2 sessions are supposed to match with each other? What happens there? In the end, what I'm trying to get at is you got to understand the data journey. So you can't really do risk assessment or risk analysis well if you don't understand what the behaviors or the whole end-to-end thing is supposed to be doing. How does each piece within the architecture work with one another? So this is a very simple ELT diagram where we start on the left where we have our sources. In this case, we're grabbing data kind of like Google Analytics where we're streaming data in. We're moving that into Kinesis. Kinesis is managing all of the stream for us, and it's eventually batching things. And if you worked with Kinesis, you know what I'm talking about. It sends that data. We're going to use S3 as our data lake. And then from S3, we have Airflow. We have DAGs that help us do these transformations, get things into our Snowflake database or get things into our Neptune database so we can continue doing things. Right? Understanding your data journey is crucial. As software testers, we care about this because what happens if something with S3 messes up? Everything downstream is now screwed up. And so we're going to make sure that our data lake is as robust and reliable as possible, so then we don't have to worry about what's going on downstream. We can keep adding tests in different places. So you heard of like unit tests, integration tests, contract tests, end-to-end tests. There's all these different types because we may want tests on each one of these pieces. We want tests that go from like extract to load, and maybe tests that go the entire journey. What happens when a session goes all the way through to the data warehouse? What does that look like? Let me make a simulation of that and test that flow. Very nice. Number 5 is preparing the data. I'll admit this is where software testers probably help the least. But what shapes does the data need to be in? What are the data types? Are there missing values or errors? In the end, poop data makes poop models. A lot of the time, a lot of machine learning engineers on my team will create these transformations, and we use Python quite a bit. So we'll have these transformations. Well, it's very easy for us to automate a lot of that and say, if you expect the circle data that's coming in to be turned into a triangle, that's a relatively easy test to write. And now, anytime we make changes, well, I can always run this test that makes sure that circles turn into triangles in this step. So we can help out with a lot of this as well. Training and validating models. Experiment, compare multiple models. I'll go through this one real quick because all the data scientists know this really, really well. And of course, using tests. Again, we try to automate a lot of it. There's a lot that is more exploratory, more kind of free form that you can't really automate, or you probably don't want to automate. But there's probably a good suite of tests that you will want to have automated. So anytime you make a new experiment, you can run that experiment through your gauntlet of tests, get some results, and hopefully be able to test an experiment faster. So validation. I'm saying validation, not testing, even though technically in all those steps, testing happens kind of throughout. But validation, we're talking about how well does the model perform against a data set it has never seen before. So let's say that the training data set, 95% accuracy, that looks high, we're all happy about that. During validation, we get 76%. This would be an indication of overfitting. Oh crap, it knows the training data really, really well, and it sucks the validation data. So Carlos, we're talking about testing, and that's something additional. I'm not talking about validation. Myself, I don't care about the accuracy. My machine learning engineers care about that. I don't care so much about that. So what do I care about? Testing the models. What behaviors does the model show? Does it demonstrate harmful biases? And I'm going to show you some examples of this, because I know some of these might be like, what are you talking about? We'll get there. Does it meet the privacy and security requirements that we were talking about before that? So in my company, we stream a lot of people's data into our stuff. And so we'll get social security numbers, we'll get a lot of PII or personal identifiable information. So before it even reaches our servers, we have to make sure that we anonymize or mask all this information. You better believe we have a lot of tests around that to make sure we don't do that. Because I don't want to be liable for the stuff coming in, right? We don't need that, so why would I have it touch our databases? Is it performant and reliable? Can it withstand things like adversarial attacks? Does it actually solve the problems we set out to solve? Which, believe it or not, when you first start the ML project, and then like a month later on, you might have deviated quite a bit. So it's a good question. Are we still solving the problem that we set out to solve? And do our customers enjoy using our ML system? Interesting questions. Number 8, deploy the model. So again, is this going to be behind a REST or GraphQL or gRPC service? If so, we can use something like requests. Combine that with PyTest. It's very easy to write automated API tests at that point. You could use Postman to test APIs as well. If it's a mobile device, maybe it's something where your model is not supposed to have internet access. So maybe we can try it on 3G or 2G or no internet. Does your system still work? Is it supposed to work in that kind of environment? Is this going to be an airplane or self-driving car? Is it going to be in a serverless function? Maybe it's a model that feeds another model. That's pretty common in a system as well. And again, risks and the way you test, it all changes depending on how this works, right? So you saw me talk about multiple things. We could use PyTest, we could use requests, we can use Appium, we can use all these different types of tools to help us test things depending on how this thing is being deployed and what's being deployed behind. And then lastly, number 9, this is you've now deployed, so now you're going to observe and operate. So terms like observability, operability, those kind of things come to mind at this point, and hopefully you keep on going. So when it comes to risk, when it comes to software testing, these are 3 big buckets that we talk about. We try to prevent as much as we possibly can, and prevention to me sounds like shift left, right? We're trying to get together as early as possible, prevent a lot of these problems. There's mitigating risk as well, because you can't just prevent everything, right? So you're going to want to mitigate as much as you can. So things that come to mind would be like progressive deployments, using feature flags. If I have my doctor that's doing the heart detection, I'll probably give it to that one doctor, tell me how it's helping you, how it's augmenting your process. Once it works well for them, let me give it to the rest of the hospital. Once it works for all the doctors there, now let's go to the whole city, now let's go to the state, and you kind of progressively deploy your stuff. That's a mitigation technique. And in software testing, we care about this as well because we don't want to just deploy to the whole world, because that might be way more impactful. We call it a blast radius. The blast radius might be really huge. Instead, we could have just deployed to one doctor, and they could have told us whether we're on the right track or not and keep moving forward. And then, of course, detection, which is probably the one that most people think about when they think of software testing or site reliability engineering or chaos engineering. Detection is usually the thing that people think about because you're writing these functional automated tests. You're writing these experiments. You're writing these things that you run it, and it will detect something and then give you that feedback. But that's only one aspect, and there's other things we try to do as well. All right, so here it works at Zillow. Anna work at Zillow? Fantastic. So this Zillow here, I use this as an example because I think they had a very interesting problem that they faced. So from someone who's on the outside, this is how I had interpreted it and many others, but they wanted to buy properties and then sell them at a higher value, right, which makes 100% sense to me, right? Buy low, sell high, make that money. Fantastic. If you have hundreds of analysts doing this for you, and they're picking all these different data points, all these different patterns, well, why can't I just use a machine learning system to do that for me then? They're looking at these patterns, looking at these data points. If they're at these numbers, then buy the property, let's do something, resell it, and make money. So if I had an ML system to do that, well, I could make money way faster than having a bunch of humans do it for me. Makes sense. And yet things went horribly wrong. So why do you think that idea was amazing? Why do you think it kind of crashed horribly for them? And if you worked at Zillow, maybe you know the answer here. But on the left here, you see it was starting great in 2021, and then eventually, I forgot how much. I think the article said that they had to let go like 25 or 50% of their workforce based on just on this problem. On the right here, this person said, I sold my house for $550,000. and then they offered it back for $350. So they made $200,000 within the span of a week just because this person exploited their ML system without meaning to. It kind of just happened. So in this article, and I'll go through this pretty quick, in this article they talk about a few different things in here, and the ones I want to point out are it was too dependent on the ML system, so they used the ML system almost entirely to do all the decisions for them. So it would buy things and then sell things completely on its own. The AI would just do this for them. There was risk from external factors. Well, in 2021, COVID happened. So as the market fluctuated drastically because of COVID, instead of pausing and retraining or just stopping it completely and say, let's hold on for a sec, they kept it on. And so it just kept buying and selling things during the fluctuation. And so they started losing a ton of money until eventually they turned it off. One of the lessons that I got from this was it was good at first, and then it got worse over time. Okay? So now comes the idea of shift right. Hopefully that's now intuitive of shift left was be as early as possible. Shift right is now software quality happens after deployment as well. So you can't just think about, once I deploy it, okay, on to the next task, move on. Well, you still have to observe it. You still have to operate it in production as well. So what are you doing? What techniques and practices are you doing post-deployment to make sure that as things change and get worse over time, as they will, how do you prevent that from happening, right? How do you prevent those drifts and things? So the MLOps movement happened, and this was, again, like a good 10 years ago in the ML space as well. But MLOps happened, so instead of it being this linear thing, very similar to DevOps, it was meant to be more of an infinite loop where you continuously be observing, continuously be iterating and learning, retraining, instead of it being just deploy and you're done. Okay, so the rest of the presentation, now we're going to talk about just very specific techniques that we can use. So the first one is adversarial attacks. I mentioned this a little bit earlier. So on the left-hand side, this is a picture of a turtle, and the model, this red bar, the model is classifying this as a rifle, or a gun, basically. It sees it as a gun, which is funny, right? Of course, it's way off, dumb model, and yet someone taught it to think of this as a rifle, right? So we can't blame the model completely. But if you were to see all the different pictures, because we can actually see what the computer is paying attention to, it doesn't care about the turtle at all in this case, but it's really interested in that finger. And it's looking at that finger really like, that's a cool looking finger. And all the pictures that it's seeing, there's always someone moving something in, and there's always a hand. Well, that's the same kind of position for a gun as well. And so it was seeing this turtle as a rifle because of that. On the right-hand side, you put some stickers on this stop sign, and the model now classifies this as a 45-mile-per-hour sign, which, if it was in the real world, that's going to kill someone, right? So these are state-of-the-art models that were way off here. And some people may say, well, Carl, it's a stop sign. No one's going to throw stickers on that. Have you seen the city streets? Right? There's graffiti on there. There's stop signs that are pink because it's been in the sun for too long. There's some that have lights around it so you see it better. Any of those things are not weird or random experiments. Those are real things in the real world that can mess this up. And if you're not thinking or testing for these things, you're going to be killing someone. In this case, the left-hand side, this is detecting this as a person. I did a great job of that. The person on the right is completely invisible to this AI system, all because they're wearing a pretty fancy square. That's the whole reason they're invisible. I have a system like this in my house right now. I tried it, and fortunately mine doesn't do this. But if someone knew that, they could get into my house very easily, well, that would suck, because I'm putting all this time and money into this system that's supposed to be working for me and protecting my family, and it doesn't, all because they wear a hoodie or they wear a square. Okay, behavioral testing. So in here, you define those capabilities during design. Sounds a lot like shift left to me, right? They also said testing behaviors gives a more accurate picture of model performance. So more so than getting 95% accuracy during training and validation, they said if you actually test for behaviors, that is more true. That is more accurate for how the model performs more than just accuracy. And these are data scientists, not me saying this. And then they also said we created twice as many tests and found 3 times as many bugs. So how did they do that? On the left-hand side here, they define some capabilities. We need to have a high-quality vocabulary. In machine learning, you can only have a finite number of words that the ML system will know, right? So if you can only have 5,000 tokens in your vocabulary, well, those 5,000 tokens better be high-quality words, because otherwise you're spending a lot of time looking at bad things. There's negative entity recognition and then negation as well. They created these test cases on the right, where the left-hand side was the test case, expected, predicted, and then did it pass or not. And then from that, they're able to grab a failure rate. So I know this is tiny, you don't need to read what it says, but each one of these rows was a capability. And the part that I really care about is they were then able to get different models and put them all through these automated tests and be able to see how did it perform against these behaviors, not just how accurate was it. So if we zoom in on one of them, in this case you have the company is Australian, that's neutral. This is a private aircraft, that's neutral. They used state-of-the-art models from Microsoft, Google, Amazon, a Bert and Roberta model, and you can see that Microsoft was perfect in this case. Everyone switched to Azure DevOps right now. Don't do that, I'm just kidding. And then Bert and Roberta, surprisingly, were the worst of all 5 of them, which for them was surprising because they thought that it was supposed to be better than the other 3. All right, and then lastly, fair and responsible AI. When we talk about fairness of AI, we're talking about fairness by data, measurement, and design. So the first part here, we have I am straight. This was 4% toxic, and the bottom one was I am gay. So all they did was change a token, which is a type of invariance testing. I am gay was 86% toxic, clearly showing a harmful bias, right? But if you're not thinking of these things, you're never going to catch this. So Google said, well, wait a second, what if we change the tokens again from other things? What does it look like? Well, you can see here the scores that they had. Well, these are easy automated tests to have now, and now we can run your new models through this every single time, tune some stuff, retrain, put it through the gauntlet again, get these scores. Maybe you have a test that says all of these, all 6 of them, should be under 10% toxicity. That's an easy test to write again. Keep going, right? On the left-hand side, we have Turkish. On the right-hand side, we translate it to English. Turkish doesn't have gender, so you go here and it immediately assumes that nurse is female and doctor is male, clearly showing a harmful bias. Casey is my friend. We don't know if Casey is male, female, or non-binary, right? As a human, I have no idea, so you can't expect the machine learning system to know either because we already have our own biases. So by design, we could do something like this, where instead of us trying to assume the context, we could then, by design, actually say, well, friend, do you want amigo or do you want amiga? And let the user decide which one fits their context. All right, with that, recap, shift left, shift right, adversarial attacks, all good things we talked about. And at the end of the day, we need better testing because we don't have a lot of it. So I'm more than happy to talk with y'all because I know it's lunchtime now, and I don't want to stop you from your lunch. But I'll be here all day today and tomorrow. We can keep talking as well. But with that, we're all done. Thank you. Thank you.
Okay, so we do indeed have a couple of minutes for questions. There are a couple of them. So, yeah, I'm trying to figure out which is fastest. Okay, so there's a question asking you, what about test data after transformation? I mean, sometimes you need to merge a lot of data source, huge amounts of data. Do you have any suggestions to check this stage?
Yeah, so, I took this off, my bad.
Could you speak in the mic at least? Sorry, just for the live thing.
Yeah, so I mean, it really depends on what you're okay with. Because like in an ideal world, you'd be able to replicate exactly what the transformation is going to be doing, right? But in a lot of cases, let's say with Snowflake, for example, Snowflake is very well known for being expensive for compute. You probably don't want to be doing that compute over and over and over again, especially if it's a big transformation or these big queries. And so usually what you'll do is you'll make a subset of that specifically for testing and then put that through the transfer, like almost like test environment transformations. And that's great for automated testing. But for exploratory testing, you're probably going to want to just use your real data that you're doing. Hopefully that answers the question.
I think that's it. Okay. We don't have more time, but you can check. You could check with Carlos on Discord or over lunch. In the meantime, thank you so very much for joining us. Thanks again, the speaker.